So it is my great pleasure to have Bao Guang with us interviewing for our position, research position, focusing on OCR. Bao Guang is currently a PhD candidate at Huazhong University of Science and Technology in China, which is located in Wuhan. And his whole PhD dissertation has been focusing on actually OCR and detecting and recognizing text in natural images, and has done a bunch of very good work published in top venues, and his code, open source code, has been adopted by several startups actually in China. So, welcome, and the floor is yours.
Thanks. Thanks for the introduction, and thanks for having me today. So, my name is Bao Guang. I'm a fifth-year PhD student. I came to the US last October to work with Serge Belanger at Cornell Tech in New York City. So my PhD research has been focused on text detection and recognition algorithms, so which is also the title of my talk today. So firstly, I will give an overview of the problem. So basically, the task of this research is to localize and recognize text in natural images. So localize is mostly output the bounding box of text, and the recognize is to output the character sequence of text. So the task is often addressed in two steps. So first, we localize text by using some text detection algorithms. And after the localization, we crop the image out to recognize the sequence. So this is also the two parts of my talk today. The first part is text detection, and the second part is recognition. Okay. So the task of detection is to detect words or sentences by oriented bounding boxes. So I will only say words from here on, but everything also applies to sentences, which is longer. We use 5 parameters to represent an oriented box, which are the xy of the center, the w, the width, the height, and the theta to the horizon. So before I proceed to introduce our method, I will first give a quick review of the previous approaches in the past. So one popular approach is based on character detection, which is very obvious. So because text is made of characters, we can detect individual characters and group them into words. So this approach has been the mainstream for more than a decade in the past, but this approach has some inherent weaknesses, as I will address later. So first, this approach is not very robust because some characters can be easily confused with some background patterns. So here I show an image. So this image has no legible text in it. But still, a character detector might detect some patterns like I, like L, like Z on the door, and maybe even more. So because of these background patterns that look like characters, this approach could be inherently not robust. And secondly, because detecting characters, we usually need annotations on individual characters, and such annotations are usually hard to annotate, and so it comes with high cost in annotation. So another popular approach, especially in recent years, is to leverage the state-of-the-art general object detectors and directly detect bounding boxes of words as the output. So, but here I show 2 images. The left one shows some general objects, and the right one is a German word. So one difference you can see is that text could be very long, and particularly in some languages other than English. And general object detectors usually have some difficulties outputting bounding boxes of such extreme aspect ratios. And also, general object detectors, they usually are designed only to output axis-aligned bounding boxes, or we can also call it horizontal ones. But text, they usually have a clear definition of their orientation, and it's best for us to detect them by such oriented bounding boxes, which is not designed in the general object detectors. So now I will introduce our method. So our method is called segment linking, or seglink. So the main idea of seglink is to decompose whole words into two smaller elements. The first element is called segments. They are small pieces of text sliced from whole words. So each yellow box, each oriented box in this image is a segment. And the second element is called links. So a link connects a pair of segments, and it indicates that the two segments belong to the same word. So in our method, we detect segments and links all over the image, and we combine the segments that are connected by links to get the final outputs. Okay.
But the model looks like a scaled rigid model, right?
Scale rigid?
Scale rigid, because you have 5 parameters: location, which is the centroid, and then the W and the H, and the in-plane rotation.
Yeah.
So it's scale rigid.
What
Because there's
do you
no
mean by?
affine transformation, there is no
Right.
homography,
Right.
you do not account for perspective distortion.
Yeah, yeah. So for now, we only consider this number of degree of freedom, but it is also possible to incorporate more, I think. Yeah. Okay. So why do we use such representation? So the key benefit of this representation is that both segment and the links, they are locally detectable. So as I show in this figure, we can detect a segment with only a local image context without seeing the whole word, right? And so it is the case with links. We don't need to observe the whole word to know that two segments belong to the same word. We only need a local context. So by decomposing such long text into smaller elements, we make the detecting, we kind of alleviate the difficulty of producing long boxes. And because these two elements, they are both locally detectable, we can make the detection fully convolutional. Now let's move to the modal part. We use a fully convolutional network to detect segments and links separately, jointly. The backbone of our network is a pre-trained VGG16 network with several extended convolutional layers. But also, other networks should also work, like ResNet. So these blocks in this figure, they are the feature maps of 6 of the convolutional layers. The sizes are respectively, the feature map sizes are respectively 64, 32, 13, 16, and so on. So if you are familiar with CN, it shouldn't be a surprise to you that every layer has exactly the half size as its preceders. But we will use this property later on, so keep in mind. So to detect segments, we employ a convolutional predictors on each of the 6 layers. So lower layers like these two, the first two, they have a smaller receptive field and they observe smaller contexts, so they are responsible for detecting smaller segments. So, but while for higher level layers, they have larger context and they are responsible for detecting larger segments. So on each layer, the prediction outputs of for the segments consists of 7 channels. So because we detect segments fully convolutionally, we just output a feature output a map of prediction with 7 channels. So two channels are for the positive and the negative scores for the segment presence. And the rest 5 are the segment geometries, which are the delta x, delta y, wh, and the delta theta. So this is pretty much like the SSD detection, if you are familiar with that.
So this delta is with respect to an anchor point?
To anchor, right.
Okay.
Yeah. The anchor is all square box.
Sure.
Yeah. Now, let's consider links. So at every feature map location, we detect 8 links. So because we also detect segment at every location, these links indicate the connections between a segment and its 8 neighbors of segments. So for example, we consider this location marked by the yellow block. So this yellow location corresponds to the yellow segment detected on the image on the right. And suppose we also have detected segments 1 to the left and 1 to the right. So we detect links for this yellow location. We detect its links to its 8 neighbors. So suppose we have now detected the link to the left and to this right, both as positive. So this will mean that these yellow segments and the 2 blue segments, 1 to the left and 1 to the right, they are connected and they belong to the same word. Okay.
In the detection phase, does it naturally do non-maximal suppression in that it doesn't generate lots and lots of candidates?
You mean detecting the segments?
If we go to the previous slide.
Okay.
So let's pick any one of the predictors, right?
Okay.
How do you ensure that you don't get lots and lots of overlapping candidates?
So first of all, the overlap between segments is fine because we will combine them later. If 2 segments, they are overlapped, but our combination algorithm will join them into a whole box.
But what if it's shift up and down?
You mean shift up between?
I mean, you have lots of them, and some are shifted like 2 pixels up, some are shifted 2 pixels down, so you might get a bounding box that is much bigger than it should be.
So we, in the combination algorithm, we calculate their average. So I think this combination should be robust to 1 segment's offset. Yeah. I'm not sure if that answers your question.
Yeah, I think Simon's question is more about for each segment detection. Or if you have the problem, because the detection score is smooth, right? So in local regions, if you shift the bounding box a little bit, it could still pass through a threshold. That's I think when we are talking about the deep network-based detector, it's slightly different.
I don't know how it actually works. So.
Yeah, that actually it's slightly different than conventional or sliding window using boosting or something like that. I think you can discuss
we can discuss offline.
Okay.
I think the filtering happens during the linking, though.
Yeah.
Like
You mean the filtering?
the NMS, something similar to NMS when you do averaging. That's like filtering for all these excessive detections that you'll have.
I'm not sure if I get your meaning, but but I will address that problem later, the redundancy problem. So if you see here that link segments are actually, for the same word, are actually detected on multiple layers. So that's where the redundancy happens, but I will address this very soon. Okay. Does this make sense to you? We'll move on. Okay. So just like segments, the links, they are also detected on these 6 feature maps. And because we detect 8 links at every location, it's again a convolutional prediction. And for each map, we output a prediction map of depth 16, which correspond to the positive and the negative scores of the 8 links at every location. So it's also done convolutionally.
Are there any shared weights here, or how is the information from the segments being presented to the link detector?
They are different predictors, but they share the same feature map. So I think their prediction should be highly correlated in
So
some
the
sense.
first several groups of VGG are common. Right.
What do you mean?
So I think another the question, in other words, is which layer of the feature map you picked up to do the prediction?
Oh, so the feature map, we picked two feature maps from the VGG16, the original VGG16. One is conv43, and the other is the convolutionalized, the last fully connected layer. So this is called FC, but it is converted into a convolutional layer. And we follow SSD to add a few extra layers.
Right.
Yeah.
That makes sense. Yeah,
yeah.
The question is about, you have these detections of segments.
Mm-hmm.
Now, when you detect links, is that based on the segments, or is that a totally separate prediction problem that you'll fuse later?
It's totally separate. So both segments and links, they use the same feature map, but they are both using convolutional predictors, but their weights are different. Yeah. Okay. So now we have detected the segments and the links, but we have not done yet. So in this figure, we see that the segments of a word can be detected at multiple layers at the same time, right? So like the two I marked with red circle. So even though we set different layers to be responsible for a different range of scales by setting their size of anchors, they still inevitably have some range, some overlap between their scale range. So there are some inevitable redundancy produced at consecutive prediction layers.
I have a fundamental question.
Mm.
Why are you using a deep net as opposed to just a normal image processing technique? Because the overlap seems pretty straightforward. Is there any fundamental problem? I mean, what is the characteristic that makes it great for using a deep network as opposed to, oh, I have this overlapping, boxes, so therefore they're linked?
Right. That's a good question. So I think what you mean is that we can actually link segments based on their geometry relationship, right? Yeah, actually we can do that. But so consider this case, if two words, they are very nearby. And now the segments of the two, and we still want to separate using different detection boxes. So now their segments will be very nearby. And it might end up we combine the two words together if we just use geometry relationships. Yeah, but if we explicitly detect, classify these kind of links, I think we have a better control over what kind of links should be connected and which should not be. Yeah.
I'm not convinced, but we can talk about this after.
Okay. I can give you another example.
I think I can believe that. I think his explanation makes a lot of sense to me, because if you consider you have two words there, like there's a slide blank. If your detection, because detection bounding box is all going to be secretly typed, right? Like the last segment of first words and the first segment of the second words could have overlap. Based on purely like a position, spatial relationship, you could merge them. But because in this training process, you have ground truths which have two separate bounding boxes there, you are not going to predict those two segments as links based on your supervision information.
Well, my argument is, if you have the bounding boxes already, you can actually do a analysis of what's in it to see the separation. And so you look at the analysis and say, okay, based on what I've seen, the separations are different, right? And so the statistics can be computed within that.
You can, but this is to me this is the one short algorithm which you don't need to take separate steps. Those are implicitly considered in the learning process. What you mentioned, these statistics are considered.
Right, but the downside is you need a lot of training data. Where does the training data comes from, right?
That's true. I think potentially he will address that in part of the.
Right. Surely will.
Is the link detection purely local? So like letter, it has a bounding box and it's looking at its left and right neighbors and deciding whether to link. Do you handle any kind of global information where my right neighbor doesn't really look like it should be connected, but if I looked like 2 boxes over and consider them as a whole, maybe it does look like it should be connected?
So the prediction is local, but I think it goes beyond the context of just a segment.
Okay.
Yeah, because the receptive field is usually much larger than the prediction target. So yeah, it is local.
So it's taking a larger receptive field. Okay.
Yeah, but I think it captures enough context and it's fine.
So I just want to triangulate these two comments because I agree that I think you have to learn something local or possibly apply some sort of complicated statistics or analysis on all of the segments that you detect to be able to fuse them intelligently. But you could also learn something very shallow. And doing something 12 layers deep or more,
Yeah, but
and pulling on VGG may, while that works, I think that thinking carefully about how to do that may end up with a much simpler solution that's more interpretable.
potentially,
anyway.
I would agree, but it considers the detection part and the linking part is sharing the feature map, right? The detection part you cannot.
You do need to tie them, yeah,
Yeah.
that's
The
true.
detection part you potentially need some deeper structure.
And you do need the scale,
Yeah.
so.
So another thing I was thinking, because I read some of the work before, if you consider thinking you have a circle type of text, your the rule-based or statistic-based linear process is going to potentially run into issue. But I think you may have examples where you can detect the text lines in a circle. Right?
Actually, I don't have such examples,
Because
but
isn't it a lattice though that he's looking at basically?
sorry.
Aren't you looking at basically a lattice? You're not looking at if something is sort of at an angle. You're taking a box and you're looking at the 8 positions, sort of. I guess if you had a diagonal. Maybe.
So
It's handled, I think.
yeah.
But this segment link
That's
approach,
what's
I feel there is a potential you can address this circle type of text, like large signs in a restaurant where you have this circle type of text arrangement.
So you can first order
The
approximation.
components are there, but you have to formulate the output space differently than you have.
Yeah, so that's the base, right? I think the breaking the set makes sense to me, but anyway, we should continue perhaps.
Okay. Yeah, I will address that later, maybe. Okay. So let's go back to this redundancy problem. So one obvious way to address this is to combine the segments on different layers separately and do some maximum suppression to remove the redundancies. So, but we have a better idea for this. So our solution is to detect another type of links, so which we call cross-layer links. So here, on the upper part of this slide, is the within-layer links, is what we have just discussed. So links, they are detected between segments on the same layer, so we call it within-layer links. The cross-layer links, they are on the second row of this figure. They actually connect segments of 2 different layers. So, for example, so for a location on a feature map, for a higher feature map, for example, for location ij, we first find its cross-layer neighbors as these 4 locations. They are 2i, 2j, 2i plus 1, 2j, 2i plus 1, 2j plus 1. So for this location, we find its 4 cross-layer neighbors on the lower feature map. And then we detect the 4 links. So the links from this location to these 4 cross-layer neighbor locations. So in this example, suppose we have detected a segment on this layer which is marked by the bigger yellow segment. And we have also detected 2 blue segments here. And suppose we have detected cross-layer links as these 2 green edges. So this will mean that on this image, the bigger segment and the 2 blue small segments, they are connected, and they should be combined later. Okay, does this make sense to you? So, so the key idea here is because the feature map, so the lower feature map always has double the size of the higher one. So we can find 4 cross-layer neighbors on the higher, for each location on the higher feature map as following these rules. And we detect the link between this location and its 4 cross-layer neighbors on the lower layer. And this will mean that this will connect the higher layer segment with the lower layer segments. So this essentially, and we detect such cross-layer neighbors across all consecutive pairs of layers.
Did you consider the use of an overlapping neighbor, like neighbors that are overlapping? Because now they seem that the stripe is the size of the box. But did you consider overlapping?
You mean the overlap between the segments?
Like the neighbors of the previous layer to be overlapping with the box of the upper layer.
You mean when we connect them, we
Yeah.
consider their overlap?
The candidates for connection. Did you consider to use overlapping boxes?
We don't. We actually don't. We explicitly predict their connection.
Mm-hmm.
Yeah, and we don't consider their geometry relationships. Yeah.
And also, how do you choose boxes? Because you have some candidates from the same layer, some candidates from the previous layer, and maybe you have some candidates also from other layers. How do you consider candidates, or you use all of them?
No, it's independent.
Mm-hmm.
The linking is a totally separate prediction problem,
Mm-hmm.
right?
Yeah.
It's actually,
Link.
Is after, I think it's done jointly.
Mm-hmm.
Yeah.
But you don't have the issue sort of, it's once it is fired up, like another box that you start predicting the links
Mm-hmm.
to surrounding noise.
Do you have examples where the words are stacked, like you have 2 words crossed right on top of each other? What will happen in that case?
Yeah, that's a good question. We actually don't have that example, but
You want to draw something?
yeah, I can draw it to show it to you. That it's in our method, it still will work.
I can just use this.
Okay. So I think what you mean is that we have a word vertically and another word in the horizontal.
No.
Not this way?
2 cross. Let's say cross is right, one above the other.
Okay. One above another? You mean
Right above the other. Yes.
this one?
Yeah, they're close enough that they may be considered to be linked.
Yeah. So actually, we will detect segments for this word and for this word. And when we link them, so ideally, we will only detect links between these pairs. And for these links, they are actually detected as negative. So there won't be links between them detected.
Yeah, the link as far as my understanding goes, I think because the receptive field is actually when you're predicting this link, it's not only taking the local information, you're taking a much larger image radius there.
but what if the kerning in the horizontal direction is the same as that in the vertical direction?
Yeah.
Yeah, and only semantics can tell them apart.
A lot less necessary, right? Like because you must learn some regularity to predict this horizontally because you have constantly may have more statistics towards this direction. Right?
But you don't have examples of that.
I don't think in this slide I have that. So
Orientation.
I think you can just consider this case. So for example, this local prediction at this region. So for example, it sees some kind of patterns like this. So where these are text and these are also text. So it actually can learn such pattern as separation of text. And it can predict the link here as negative. I think it should be able to be achieved by a classifier.
Only if you have enough data.
Right. I will address that problem very soon. Yeah.
And the early layers are fixed through all of this. The first like 5 groups or whatever that you have with the featured maps are all fixed. Come from ImageNet. Or do
What do you
you-
mean by fixed?
Do you fine tune?
Yeah, I fine-tuned that.
With feedback from both the segments and the links?
Yeah, I will talk about training very soon. Yeah.
Because it seems like there's a mismatch here. When you do cross-layer prediction and you backpropagate, if you're using max pooling, then there's potentially information from multiple pixels that are in the receptive field in the previous layer. But you'll only propagate through one, and you don't have the same prediction, the way that the supervision is being fed up to the previous layer from this prediction. I don't think you have the same, well, maybe there's the same. You see what I mean?
So I think, I will clarify one point first. So the cross-layer links, they are actually detected at this feature location,
Okay.
and they're not detected here.
Okay.
So at this location, we detect 4 links using the features at the higher layer. And they correspond to the imaginary links between the high layer and the lower layer. Yeah. I don't know if that answers your question.
Yeah, I need to think about it.
Okay. Yeah, it's all supervised training, as I will talk about very soon, and it's very straightforward. All right. So here I show the complete picture of our model. On each of the 6 layers, we detect segments. We detect within layer links. They are the green edges between segments within each layer. And we also detect the cross links. So here I show the link that go across 2 different feature layers. So they connect segments up to different layers. So after we detect all these elements, we perform a depth first search on the graph of the detected segments and the links to find the connected components. So in this case, we will find 2 connected components. So because these segments, they are all connected in some way. And this one, they are connected. So we will find these 2 connected components. And then we combine them using some basic geometry rules to get the final results. So basically, the combination is we first find the average of the height among a connected component, and we find the length, basically the left and the right extent to which the segment is placed. And the orientation is also averaged across all segments. And at last, we will output such boxes. Okay, does this make sense to you?
What do you do if the input is an 8 megapixel image?
8 megapixel?
Because normal,
You mean a very large image?
yes,
Um,
because,
yeah,
it's
so
getting much more sophisticated.
you mean in our method, we would scale that image to too small?
Yes.
Yeah, so here I show a 500 by 500 images, but actually, because these are all fully convolutional, we can apply it to any different size. So if the image is larger, we can just fit it into this pipeline, and it will still work in this way.
It's just a runtime issue, right? You can do even 12 megapixels, not an issue, I think.
Yeah.
The idea of fully convolutional labs, I think, actually I just said, because you just consider, because it is fully convolutional, if the image is larger, I'm just going to have more output. the output map size is going to be large. Think about that. Because I can shift this 512 by 500 square window inside my bigger images. Essentially. That's the most straightforward.
Yeah, but it's a windowing approach, right?
It's a lot less a windowing approach. In the case, it's just you can consider like because it is fully convolution, right? So you can replicate the computations spatial, essentially. You can just replicate that.
Yeah, this is a long conversation that I will.
Yeah, maybe he can
Right.
perhaps explain that in detail later. So.
Okay. All right, so this is pretty much of our method. So here I put things together to show that the convolutional predictors actually simply outputs a map of depth 31. So which consists of the prediction of the segments, the within layer links, and the cross layer links. So the first 7 channels, as I have mentioned, they correspond to the segment scores and the segment offset. And the within layer links, they consist of 16 channels, and the rest 8 for the cross layer link scores. So here I use dashed line because this part is not used in the lowest layer because it has no lower layer, and so we don't detect cross layer links on the first convolutional layer. Okay, so these are just the output of the convolutional predictor. So they don't share weights, of course. So they are actually predicted separately. But in computation, they can be just achieved using one convolutional operator. So it can make things very efficient. Okay, we haven't talked about the training yet. So the training is supervised training. We have labels for all these segments and the links, but obviously we don't have such annotations. So we actually generate these ground truths from the ground truth word bounding box. So usually this dataset comes with this word bounding box defined by maybe a polygon or oriented bounding box. So, and we also have these anchors all over the image. So we generate the segment in this way. So first, for each anchor, we rotate the word bounding box along its center to the horizon, like this. And then we crop the word bounding box, the rotated word bounding box, to remove the part to the left and to the right of the anchor. And then we rotate this box back with the same theta orientation so that we get this one as the ground truth segment. So the segment is basically a small slice of the original word bounding box with the same orientation, the same height, but different width. Okay. So this is for the segment, and for the links. So a link is simply determined by if 2 anchors they have corresponding, they are matched to a word. They are matched to the same word, we label it as positive, otherwise it's all negative. Okay. So do you have any problems with this process?
So you have a lot of segments for each word, right? Possibly hundreds.
Yeah, not so many, maybe dozens of.
Dozens. That's based on how you quantize the default box, or how you
Right,
set up the default
right,
boxes.
right.
What was that?
I guess it's mainly the spacing of the anchor point.
Yes.
Yeah. So usually all over the image, there are all over the scales, there are like a few thousand anchor box, and for every anchor box, it's matched to a word, or matched to none if it doesn't match to any of them. And the links is even more like a dozen thousand. Yeah, but it's fine. It's not too many for deep network.
Did you find that segments usually matched closely to one with characters, or was it much more sort of arbitrary, just sort of random segments that connect together to form a word? Like, can it be multiple characters, or it looked like in the example you had like some segments are like 1.5 characters. with some overlap. Did you just do any looking to see what the segments actually represented in terms of the image?
Yeah, I can show example later. Usually it's just one character.
It's about one character.
I would say
an
you're.
example, or if that's actually how it was in practice. That's, I guess, the question. But
It doesn't.
Sounds like you answered it.
From this one truth generation process, I wouldn't expect a single character because you have low control of the slicing.
That's
Yeah,
what I
yeah.
figured as well. Yeah.
Yeah, you don't have control over that, but usually it's like 2 to 3 characters maybe.
Depends on spacing.
Yeah.
It depends on how the character width. You know, different fonts may have very different appearance. Yeah, we actually aim to learn that by itself. Yeah.
So, what's the data set you actually use for
Training?
training?
Yeah, I will talk about it very soon. Yeah.
They're hosting a grand challenge in ICT.
I see. Yeah.
Yeah, there are several standard benchmarks there. Okay, so here, as you see, the only training data we need is actually the bounding box of the word. We don't need, we generated all the segments and link annotations from it.
Because I do have one more question. Are the boxes always square? These segment boxes that you're generating? Are they always
Segment
square?
box? No, they're not square. So here you see if the width is same or less than the anchor, but the height they could be larger or smaller than the width. So the segment isn't necessarily square. But we set anchor to be square.
Okay, how much variation can there be between the width and the height? I have a follow-up question after this, so that's what I'm getting at.
Variation usually is not too much. Yeah.
So I guess what I'm imagining with the segment approach is that if you miss part of a word, like there's no segment that captures part of a word, then you'll miss detecting the word itself, because you're not detecting entire words, you're just detecting these smaller segments and then linking them, right?
Mhm.
So if part of a word is occluded, where you may be able to detect the word as a whole, but you'll miss part of it and it'll get broken up, is that a problem?
I think it depends on how much if it's occluded. So if it's heavily occluded, it might end up with 2 different words detected.
Yeah.
Yeah,
and-
that's could be the issue.
Okay.
Yeah.
And do you think that's a problem, or can that be fixed with something?
I think it's still hard to fix it under this framework. I don't think any framework is very good at that, because 2 occluded words just look like 2 different words sometimes. Yeah, I think
Depends on the amount
it
of
may need
occlusion.
some.
I understand.
Yeah, it may need some semantic understanding over that, I
Okay,
guess.
that's all I was wondering is, yeah.
Yeah,
that
yeah.
problem.
If your language model allows like reasoning for solution, potentially you can address that. But still, that's a difficult problem. You handle
I
that. You
didn't-
generate false positives.
Yeah, I wasn't imagining severe occlusion, but it's fine. We can talk about that offline.
Okay. So for the training, we employ the standard stochastic gradient descent to train network with the with the annotations. We use the supervised learning scheme. So because for both segments and links, the number of positive, the ratio between the positive examples to the negative is very small. We only have very few positive links and segments. So we use a online hard negative mining for both segments and links separately. So the online hard negative mining is basically pick up the hardest negative examples to train with together with the positive ones, so that the training data won't be overwhelmed by all the negative examples. And we also use all the data augmentation tricks we borrowed from SSD. Yeah, it's called single shot multi-scale detector. It's a very popular detection method.
Yeah, I know.
Yeah, it's not.
Stereo, it's not square differences, so that's why I asked.
Yeah. I have been asked many times about the SSD.
This detector was proposed like 2 years ago, maybe.
1 year maybe.
1 year.
1 year.
2 years.
Yeah. Yeah, you may find that I mentioned SSD a lot, but actually our method is fundamentally different from them. Yeah, we just use a lot of techniques from them. Okay, so our model is evaluated on the IGDAR 2015 incidental dataset. Sorry, I forgot to mention one part. So we actually train our model on a synthetic dataset, which consists of the synthesized examples, which is made by rendering random text with random color response on natural images that does not contain text. So this is not done by us, it's done by a group from Oxford. We pre-train our model on this dataset. It consists like 80,000 images. And then for each different benchmark, like this one, we fine-tune the pre-trained model with the few hundreds to few thousand examples. So we first evaluate the model on the IGDAR 2015 incidental dataset. So images in this dataset contains text of different scales and orientation, and the background, as you see, are usually very cluttered. So here are some examples, some detection results. The yellow box are the zoom-in region of the image. And as you can see, the method is able to detect text very accurately over this very cluttered background. And it can actually separate words that are very nearby. As you see, they are almost touched words.
So what's the number below each image? Means the number of statistics from this image?
Yeah, from this single image. So there we call precision and the F-score from this single
that
image.
Means you set a different threshold?
No. It's at the same threshold.
Okay.
Yeah, it's
just calculating the statistics from a single
Yeah.
image.
The model is evaluated with the same parameters.
Which cases you think are the most difficult ones for this method?
Sorry, which different?
Cases?
Failure case.
Failure case? Okay, for this dataset, I think one failure case is very large text actually, because I think there are some issues with detecting those very large texts. Maybe it's not covered by the receptive field, or and also.
Do you think in this case you could detect the size of the salient text and then maybe pad around so that when you scale to be 500 and 500 has the right size? So maybe you can pad the image or crop it.
You mean downsize it?
Either you can either pad, add the margin, or
Shrink the
crop
size.
it.
Yeah, of course we can do that.
So then if you scale, like you detect basically the critical, the salient text, and then you expect that it's within the right, margin.
Yeah. I think we can do that. Yeah, but we still want to keep our method general in this case. Actually, regarding the size, these images, they are not detected, they are not resized to 500, but to like 1,000 times 700. We basically keep their original aspect ratios. So because our model is convolutional, we can just apply to any size basically. Yeah.
We do single scale evaluation.
Single scale. We only have one shot. So efficiency is also our concern in this method. I'll talk about later.
So if you build an image pyramid, you can literally potentially have higher, I don't know, maybe recall.
Yeah, if we do that, we actually don't need to use the multi-layer outputs in the model, and we can make things even more robust, I guess.
Versus you use the feature pyramid essentially, because you are using VHG, right?
Yeah.
The downsample rate is always half, so it's basically a feature pyramid, like lower unit pyramid.
Right.
Yeah.
Yeah. Okay. In the numbers, our model significantly outperforms previous state-of-the-arts. Actually, as of the time of submission, it's no more the state-of-the-art now. But yeah, we actually got some good results at the time of submission.
So what's the ranking of irregular? I was watching the table now. I think that table refresh very fast, especially with
Yeah,
results from
I think you are referring to the online competition
Yeah.
table. So there are some methods that is already comes near to 90 F measure, but they don't disclose their method
Sure.
so far. And so actually there are a lot of ways to improve performance, maybe using multiple models. So as you know, the best results on MS COCO in the papers are actually very lower than the competition results. Yeah, so.
So these are discrete results for a set of retrieved words, as opposed to like bounding box overlap truth values.
So sorry, I didn't catch
So what
that.
I'm concerned about is go to the previous slide.
Okay.
The bottom center one, the patch. Would you consider that a positive result for the word, even though the bounding box doesn't include the entire word?
Yeah.
So is there a threshold basically that determines like, yes, it's positive, and then you return the word, and then you calculate statistics from that?
So this one is still considered as positive because it matches the ground truth. Yeah, I know it's misses some part. Yeah, but this
But it
evaluation.
missed the word sale below it.
Right. Well, yeah, the
Oh,
precision's
the
not
sale?
perfect, so I that part I get. I can focus more on the word recognition side, so I'm thinking like to us that wouldn't really be positive because I probably can't detect the word because they're only half of it is there. But
Yeah, this is largely detection.
yeah, no, I know.
Yeah, we did miss the sale, and for some reasons.
I'm just saying, even though only a little bit of the box is
IOU
missing,
is
the
greater
semantics
than
are such that it's
0.7.
almost not a positive detection.
Isn't that an IOU is greater than 0.7? Or
Sorry?
The threshold is
Oh,
like IOU is
0.5.
0.5.
Yeah, it's their standard.
That's the standard.
Yeah.
Yeah, I don't think the standard is perfect, but yeah, it's
I'm holding, so
out of the scope.
I was curious because I don't usually focus on the detection side, so I just
Okay.
have questions about evaluation.
So we are approaching to 1 hour. So we have half an hour. So let's move
Okay.
leave some of the questions to one-on-one, and hopefully we have a little bit of time asking questions towards the end.
Okay, yeah. Okay, I will speed up a little bit. So here are some other images on a multilingual dataset called MSR-ATD 500. So in the first row, we visualize the detected segments and the links. The segments are visualized as these small oriented box. So as you see, they usually are several characters in one segment. The edges between the segments are the links. So in the second row, we show the combined boxes. So we can see that by decomposing the long text into smaller elements, we can actually detect this very long text effectively.
Timmy, I think that's one example you mentioned, the two parallel ones. Which are
Yeah.
But it missed that Darling Street.
Yeah, that is straight. You
This
missed
one?
some, yeah.
Oh, it's not missed though. I forgot to. There, as you see, there is a very pale green box here. So when we do these slides, I put some new box here to make it clearer. But it is actually detected. I forgot to fix that.
Are you able to see it?
Yeah. As you see, yeah. We already have
There
this.
is a box.
Yeah.
That was confirmed just there.
Sorry.
It's just if you forgot to put that new box there. Just,
Yeah.
there is-
I put this new box to make it looks more clear. So on this data set, we also achieve the state-of-the-art performance. And more importantly, since our model is fully convolutional, it runs very fast compared to the previous work. So
This is the MSR he did assessment. I don't know.
yeah,
500, okay.
yeah. So on this data set, we evaluate on 700 by 700 images, and it runs about 9 frames per second, which is significantly faster than the previous state-of-the-art. So to conclude, the most important advantage of our method is that it can detect long lines of text in arbitrary orientation. And because of this, our model is able to detect text of languages that don't have space between them. So like as I just showed you, Chinese, they don't have, you cannot detect them by words. So in terms of detection accuracy, we are able to achieve state-of-the-art results on several benchmarks. And lastly, since our model is fully convolutional and it does one-shot detection on multiple scales, it's very fast.
That 20 frames per second is using GPU,
Right, using single GPU, Titan. Yeah.
With at least 8
Sorry.
gigs of memory, probably, right? Or at least 4 gigs.
using GPU memory.
I didn't calculate that actually.
So what's the memory size of the GPU?
So it's 12 gigabytes Titan X. I'm sure it won't. That won't be necessary for one image.
I think you need 4. probably
Maybe 4, yeah, probably. Okay, now I will move to the second part. I will be a little faster. Okay, so here the problem is to recognize character sequence from cropped text images. So traditionally, this problem is addressed in multiple steps, including character detection, character recognition, and character grouping. So, but obviously, using multiple modules makes it harder to train models. So, there could be some penalties between this when you go through multiple modules. So our goal is to propose a network which we call image-to-character network, so or I2C-net. So this network, it can recognize its character sequence directly from images, and it can be trained end-to-end with image and text. So we just use one network to produce character sequence directly from image. So we don't need all those steps of modules. So here I show the overall architecture of the I2C-net. It is an encoder-decoder structure. The encoder extracts a feature sequence from the input image, and the decoder output the character sequence based on the encoded feature sequence. So next I will go through this structure step by step. So here is the input image. It is resized to a fixed size, 32 by 100. So because we, in this task, we only concerns English words, so this size is suitable for most English words. And then we employ 7 convolutional layers to extract a feature map. The configuration of this network is similar to that of VGGNet, but we made some minor adjustment. We use, in 2 of the pooling layers, we use a 1x2 stride pooling, so that we have a higher resolution in the horizontal direction. Because we want to distinguish some thin letters like I and J, we better have a rectangular receptive field for them. Okay. And next, after we get the feature map, we converted it into a feature sequence. So this conversion is done by splitting the feature map along its columns. So suppose we have a feature map of size d by h by w. D is the depth. We split the maps along its columns, so we get a sequence of w vectors along the width. And each vector has d by h dimensions. Okay, did you get that? So basically suppose we have this feature map, we pick up one column of it, and we as the first feature vector, and then we do the next.
So it's like a sliding window just with one.
Yeah, you can imagine a sliding window, but actually it's just split the feature map in 2 vectors. Yeah.
They have overlap, right?
They don't have overlap.
They don't have overlap.
Yeah, they don't have overlap. So now we have a feature sequence. So the feature sequence would describe the image from left to right because of their receptive field are arranged from left to right on the original image. So then we let this feature sequence go through a bidirectional LSTM, shown here. So that the LSTM is to capture some long-range context along the feature sequence. So the BLSTM gets this input and it outputs another sequence of the same length. So this sequence has larger information, has larger context compared to the input. So, but after all, we have a feature sequence that describes the image from left to right. Okay, so this is the encoder part. Now, for the decoder is an attention-based character generator. It works iteratively. Every step, it calculates a weight value for each vector in the input sequence, and to determine which part of the input to focus on. And then it outputs the next recognized character based on the input sequence and its internal state. So it works iteratively. So first, it would output a G character, and in the next step, it would output I, and so on until S. After S, it will output an end of sequence symbol, which means the end of generation. So this decoder model is actually a classical one. It has been used extensively in machine translation and speech recognition. But we were the first to use it in this image text recognition problem.
Sorry, your BLSTM graphic is impressionistic, right? In that you have connections going to out of an output from your LSTM going into the input of another the next step, but it goes in both directions, right?
You mean the BLSTM?
Yeah.
Yeah, it goes both direction to analyze text to the left and right.
And up and down too?
Up and down?
Are there any connections between vertical, or is it this just?
Depends on your bounding box.
No, there's no vertical. Yeah, because we after we get the feature map, we pick a column. So all the feature in that column is taken into a vector.
I think there is a question. What if the text is vertical?
Oh, if it's vertical and it's written and the character are arranged in this orientation, we just rotate it. But this currently only works for horizontal ones. Yeah. Okay. So this is the whole model. It takes the input image and output character sequence. And also note that this model is end-to-end trainable. So we just feed the input training images here, and we feed the ground truth text on the top, and it will train by itself.
I'm curious about the generator GT. So you use the current state H, you use the previous word ST minus 1, and you do you use some context from all the previous characters?
Yeah, the recurrent network it can capture some context from the previous output.
You mean the hidden state H captures the context? The H?
The H?
You have H, right?
Yeah.
So
it's a recurrent network, so it keeps its previous state all the time.
Because I've seen some models that they use the previous character ST minus 1, they use H, and they use also a global context of the characters that we have already generated, weighted by the attention. But you don't use other contexts other than H.
So here it also observes the whole sequence all the time, so it can decide.
You trust H for context, and you do not explicitly, use context for generating GT. I see. Okay. And for attention, you use some kind of cosine similarity. What kind of attention you have there?
Attention? Let me think. It is like cosine similarity. We don't normalize it to to one norm. Yeah, it's basically inner product similarity. So after inner product, we do some soft max over the output to get a weight vector.
Inner product, but the inner product is between the state H and every character, or what else? You have a inner product between H and what else?
An inner product between
H and what else? You attend which characters?
I don't know if I catch
He's
that maybe.
asking if you were taking the inner product between H and which other way?
Oh, you mean this H?
Yeah.
The attention. Yeah, the attention. I think it's H. It takes concern H with some of its internal state. So actually, H combines multiple vectors. It's a tensor actually, and the attention module has an internal state, and it uses this internal state to calculate a output score with every column of the H.
Okay.
Yeah, we can.
Let's move forward.
Yeah, maybe we can talk about.
This question as well.
Okay. So for this model, we random initialize it on all layers, and we don't do any pre-training. We just directly train it on a 9 million also synthetic text dataset. So this dataset contains all images like this. Oh, sorry, not this one. So it contains, so this is a synthetic text dataset. I don't have an example. We use Adam optimization to train from scratch. So here I show some examples. So for each image, I visualize its attention weights of all the generation steps. So at the T step, its attention vector is visualized on the T's row. So as you can see that for every generation step, the attention actually attends to a location that corresponds to the character location. So effectively, it is doing some kind of text detection implicitly. And all these images, they are correctly recognized. So we also evaluate the performance on some public benchmarks. And we achieve all state-of-the-art or very competitive results. Okay. So this network, it works well in normal cases. So, but still, it fails on some texts which we call irregular text. Most irregular text, they are either perspectively distorted or they are arranged in a curved shape. So they could be the results of imperfect detection, or they could be their camera angles, things like
So
that.
Can you not get, once you get the bounding box, can you not rectify it for the perspective cases?
You mean, yeah, we can do that. Yeah, if we can detect the text by ourselves, we can actually rectify it using the detection information. But for this task, we only have the image. We don't do detection here. But I think
Maybe if you can post-processing, if you assume the text are with the same height,
Right.
you can eventually figure out the perspective joint to rectify the text back to the correct aspect ratio. But without that assumption, I think it's going to be difficult because some words, for example, the first letter could be really like capitalized and big, right?
Yeah.
Higher than the rest of the things.
Yeah, but I look at the text, there's not a strong perspective effect on it. Like Fishman, there's hardly any perspective effect.
Are you kidding me? Starbucks, it's like so much of perspective there.
No, I'm talking about Fishman, for example, the one at the bottom row.
But in this case, I would say like you need a pre-processing step to rectify the perspective geometry. That part, I think what he means is that if you fit this image directly into the rectifier, it's not going to work.
Right.
Right. Yeah.
You can post that in some of the pre-processing steps, which cannot be handled in that way, essentially.
Okay. So So to address this irregular text problem, we propose to rectify the images before we recognize them. So here we adopt a nonlinear transformation, which is called thin plane spline, or TPS transform. The TPS is able to warp image in a nonlinear way based on the two set of fiducial points. So suppose we place the fiducial points along the upper edge and the down edge of a word. And we can warp the input image to a new image that has a regular text. So now the problem is how to, if we can place the fiducial points right. Okay. So in our work, the rectification is carried out by a network called rectification network. It is based on a framework called the spatial transformer network. It first predicts the positions of 20 fiducial points via a CN model. And then it computes a TPS. So here is the CN model. It's called localization network. So it outputs a fixed number of fiducial points. So suppose they are detected in these positions. And then we, in these two modules, we calculate the parameters of the TPS transform. And then we warp the image and with the TPS transform to get a new image. So this framework is called spatial transformer network. So the unique characteristic of this network is that all these modules are differentiable. So we can actually pass gradients through the sampler, through the gradient generator, all the way to the localization network. So what this means is that we can actually train this network along with some other networks. So here is the complete picture of our model. We have a rectification network here, and we have the I2C network we have just discussed. And we concatenate them. The first module takes the input image and output the rectified image. And the second one output the recognition sequence. So in this way, we actually don't need to annotate these fiducial points. We don't need to annotate manually their locations, but let the network learn how to predict how to place the fiducial points by itself with some proper initializations. And all these modules, they are trained from scratch in this end-to-end network.
Yeah, but this will rectify one.
Mm-hmm.
This will rectify one word.
Yeah, one word. Yeah. So this task only concerns single words. Yeah.
The input is already cropped image, not the original thing image.
No.
The input to this.
Yeah.
That's the output of his detector,
Yeah,
is the
that's
input
output
here,
of the
which is going downstream.
Yeah. So it doesn't matter how many words in the original image.
Okay. So the rectification network further brings some improvement to the I2C network, especially on some data set that contains many curved text like the IIT 5K. And on some data set that is focused on irregular text like this data set, it's called SVT perspective. It's made of perspective text. And the other is called Qt80. It's all curved text. On this data set, we show some significant improvement. And here, I will show how the rectification works. So we show the rectified images on the second column of these two tables. The first column is the input image, and the fiducial points it detected. So after it detects the fiducial points, it outputs a rectified image, as in the second row. And to the prediction, the output is in the third row. So if it's in green characters, it means it's correct prediction. Otherwise, it's wrong.
Just curious if what's, I guess, for example, for the last row,
Mm-hmm.
the rectification doesn't be the same to have done much.
Right. Yeah.
So Literally, that also saying if you input the first image into your level, it's also going to recognize it. Oh, there's some errors. Okay.
Yeah,
Win-win.
I guess it's still hard for the recognizer to directly recognize the input.
I see.
Yeah. So here, as you see, it fails to rectify this very curved text. Yeah, but it still kind of alleviates the recognition difficulty for these images. But the spirit here is we don't annotate these visual points, but let it learn itself. So it's actually I think it's quite amazing that it learns to place these visual points just along the upper and the lower bounds here.
That's like hidden edges, right? Like a hallucinating.
Yeah. Right.
This has some interesting elements there.
Yeah. Yeah, so the training of the visual points is totally not controlled. But in some of our recent works, we also try to incorporate supervised training data for these visual points, basically from the synthetic data. And now we can deal with such examples very easily. Yeah.
So what's the ground truth incorrect for Mercator?
Which one?
The top one, Mercator.
EA.
Oh.
The ground truth is MAR.
I think you have.
Oh, okay. Sorry. I think it's a typo. Sorry. Yeah, thanks for. Yeah, sorry. It's in the paper. Sorry. Okay. So that's pretty much of my talk. I'll give a conclusion. So I think the key ingredients of a good text reading and the text detection recognition algorithm, the first is to have a good representation that capture the spatial characteristic of text. So despite that we have all the very strong general object detectors, but still text has its own spatial characteristics. And if we can capture those characteristics right, we can have some improvement over the general object detectors. And also, it's almost always good to have end-to-end models to output directly from image and can be trained with ground truth annotations. So like in the recognition part, we use end-to-end models, and it makes the model easier to train. Also, it outperforms a previous method. So, okay. So in the future, I might consider apply the segment linking mechanism to some general object detectors, like instance level segmentation. I also am seeing some works that has related idea to this. So that's one way I'm looking. And also, I'm thinking of combining the detection and the recognition into just one single network. So for now, there are still two different separate networks. There are some efforts in this, but so far they are still just a concatenation of two networks of very different modality. Yeah, that's basically all today's talk.
So I think we only have several minutes here. My last question is: have you ever done any end-to-end evaluation all the way from detection to
Yeah, we have done that.
What's your performance on that?
Yeah, so that was done by my lab mate. So we just simply combine the detection algorithm with the recognition and evaluate on IGDAR 2015.
Sure.
And by the time, I'm not sure if we are still the state of the art, but by the time we submit, it was much higher. It has much higher performance than the previous one.
Sure.
Yeah.
I think it's also amazing, like for text detection, I think the ICC with just a summary text-related paper, like the acceptance rate is much lower. Yet he can still push for publication with the ICC partner. I think it's great.